inserting into a binary search tree, and we did finding or searching for a node or a value in a binary search tree. Today we'll continue by deleting a node given a value, okay? So we'll start off with our example here, 12, 5, and 32. Can everybody see my iPad screen?
Yep.
Yep. Right.
Yeah.
Great. And we all have paper, pen to write on?
No.
Yep.
Uh-oh. Okay, I do now.
Okay, cool, perfect. What are the values? We had 5, right? 5. What was 5's left child?
No, it was 12, and 5 was the left child, 32 was the right child.
12, 5, 32. Awesome. And by the definition, what we have here, a binary search tree, again, the current node, its left value has to be smaller than its own value, and its right value has to be greater or equal to the node's current value. Everybody with me?
Yeah.
And a binary tree itself has at most 2 children. Okay, so here 12 has 2 children. Great. Let us build out the tree some more. Somebody give me a value for the left of 5 and the right
3.
of 3.
And 15.
Where would 15 go?
To the right.
To the right here?
Yeah.
Somebody else, is that a valid binary search tree?
No.
I think it would go to the left, a left child of 32, right?
Oh, we have to do all the left children first, right?
Well, 15 is greater than 12, correct?
I don't get it.
15.
Oh, everything on the left side of 12 has to be less than 12.
Exactly.
Yeah.
So 11.
Would that take the place of 32?
So 11, very good. 1 second, Eric, what are you saying? You're saying 15 goes to?
I'm asking, like, would it take the place of 32? Or
Well, if we have to, actually it wouldn't based on, it would just go here. Oh my, sorry. 15 would go here.
Oh, okay.
And 12, what number do we say? You said, Tiffany?
11.
11. Let's fix this. So,
Is that a 13 on the bottom left?
that was a 12. No, 13, 15.
It's a 3, not a 13.
Oh, this guy.
Okay,
over
that's
here.
a 3. Okay.
This guy here, sorry, let me fix that so we're not getting too confused here. This guy is a 3. Yes?
Okay, got it.
Great. Okay, let's continue on here. All right, we have 5 values to go. Somebody else give me a value?
40.
40. Okay. Somebody else give me a value?
50.
What is the number?
13.
13.
I said 50.
50. Oh, sorry.
21.
50.
21.
21 goes here. Okay, 2 more.
Don't forget 13.
13. Well, 13 cannot go where we are now. Yes, it can. 15, 13.
Yeah.
Okay. 1 more. Somebody else. 1 more in the back.
What did do?
24.
24.
Yeah.
24 cannot go to the right of 32. That's not gonna work.
It would have to be like
35.
30.
35.
Yeah, something
okay.
like that.
Cool. Thank you. Awesome. Great.
Is
So
that
here-
because of the 32?
Yeah, because of the 32.
Okay.
Exactly. This is good. This is a good exercise. Because of the 32, we couldn't do, what is the number?
24.
24 is less than
24.
30.
It would have to go to the left of 32.
Okay.
Right? So we'd have to put it in the left subtree. And to review, this is good. So to review what a tree has, here we have the root. Right? At 3, this is a leaf, because a leaf doesn't have any children. So all those here at the bottom are leaves. Okay. Great. And the subtree, the right subtree of 12 is this here. That's the right subtree, and the left subtree would be this here. And this is subtree, left subtree of 12, and this is the right subtree. Cool. All right, with deletion, there's 3 scenarios of deleting, right? Can I scroll down?
Mm-hmm.
So in deleting a node, there are 3 scenarios. One, there's no children, right? In the case of like any of the leaf nodes, if we want to delete them, we just delete them, right? We delete them and there's nothing else to worry about. Next scenario, 1 child. An example of a node with 1 child, well, not 5, actually, we did not do one with 1 child. Let's expand on that. Let's make 50 have 1 child. 50, let's say 80 or 65. Okay. So here 50 has 1 child. And next scenario, where it has both left and right children. Right? In that scenario here, 5, for example, has both a left and a right child. 32 has both a left and a right child, right? So there's more complexity there when you're deleting a node with more than 1 child, right? Or 2 children, right? There's more things to do there. Okay, great. So let's go through scenario number 1. Well, if I'm trying to delete, everybody still with me?
Yeah.
Good. If I'm trying to delete 65, right? Well, 65 currently has no children. Actually, let's make this even simpler than that. Let us make this simpler. So for our scenario where there's no children, for example, if I have a tree with a value 10, right? That's a tree, it's valid. It has 1 node, it's 10, right? If I'm trying to delete that, the way we would approach it, this is root. I'm getting, 1 second, I need to mute some people. I'm getting some feedback. Mute yourselves if you're not saying anything or have any question. All right, awesome. If I have a root here, it has no children. I have a tree. This is a tree. This is the root. There's no children, right? There's no children. I want to delete 10. Well, to delete 10, I would simply say root equal to nil. Okay? I say root equal to nil. This is gone. Everybody with me so far?
Yes.
Yeah.
Okay, so this is our first scenario where there's no children. I just delete the root, or I set it to nil. Our next scenario,
Wait, sorry, I do have a question. For the third one, you said both left and right children.
has
what?
both left and right child.
Oh, those are the three different instances where you would have to make a function for deleting. Okay, got you.
Yeah, those are all the scenarios we have to cover in order to say, yes, we have a function that deletes any node in a tree.
Awesome, got it. Thank you.
Very good. So we just went through scenario one, the simplest scenario. Root, you're trying to delete it, you just set it to nil. Everybody with me? Yes?
Yeah.
All right, cool. So let's go on to scenario two. So this is one. Let's go to two. So in two, we'll just draw a simple tree. Here we have one child. I'll say this is 7, this is 1. What are we trying to delete? Well, we're trying to delete 7. Right? I'm trying to delete 7. 7 is the root. So far, so good?
Yep.
Okay. So what are we doing here? Well, we'll say root is now root dot left. Okay. So root now is no longer root here. Root now represents 1. Any questions? Okay, good. Let's go to our third. Yes, go ahead.
Does this mean like in the process we would always check left first?
In the process. Well, we have to
Yeah,
check
like
both. We have to check both left and right. But if we see 7, we'd say if left equal, we've gone through a scenario where if it has 2 children or not. If it doesn't, then it has left or right. In our scenario here, it only has a left. So we have to first check to see if it has a left. If it didn't have left or right, we'll just delete root.
Okay.
Right? But since it has a left, only has a left child right now, we'll make left now the root.
Okay.
Right? We could have done that the reverse way as well and say like have 7 here and 7 has 9. And if we want to delete 7, what happens now? What do we want to do? What's the code for it? Root is what?
Root equals root dot, right?
Very good. All right. Cool. Eric, does that help you?
It does, but I think you're gonna answer
Yeah, so
in the next part.
Yeah, through the code we'll be checking is it does it have children? If it has children, does it have both children? If it has both children, we have to do scenario 3. Right?
Okay.
If it only has left, well, if it doesn't have both children, right, it has left or right. If it doesn't have left or right, then it's nil.
Okay.
All right. Moving on to scenario 3, which is a bit more complicated. Not a bit more complicated, the thing is more complicated. What do we do when we want to delete a tree with 2 children? Well, let's draw an X tree instead of us going back and forth here. So 10.
Wait, is there a difference between? Oh, okay, never mind.
What's your question?
No, because when I thought you were just gonna stay at the 2 children. When I saw you making more children, I was gonna ask if you would have to would I have to delete, go through and delete each one that has 2 children before being able to finally delete the root node that has all of these?
Yeah, we have a bit of work to do. That's why I'm trying to draw a more robust tree as opposed to just keeping it simple.
Right.
Yeah, because we have to handle, there's a lot of other cases we have to handle. Okay?
Gotcha.
Very good. So this is good. I'll even make that a bit wider. I think we're good at this point. Okay, cool. So let's fill in numbers here. I'll say 8 here. I'll say 1 here. I'll say 9 here. I'll say 32 here. I'll say 20. And I'll say 18. 18. And here I'll say 40. I'll say 39. And here I'll just say 51. Okay. Right. So the question is, now we want to delete 32. Right? We want to delete 32 now. What do we do? Well, to delete 32, we have some things to do. For now, we'll look at, remember I said we have subtrees here, right? So 32, the subtree of 32, the left subtree of 32 is here. The right subtree of 32 is here. Okay. And those are the left subtree, and this is the right subtree. Okay. I want to delete 32. What do I do? Well, 32, to delete 32, I'll look at the right. Again, we could look at left or right, but for now, we look at the right side. In the right side, I want to get the minimum value. What's the minimum value in our right subtree for 32?
18.
Sorry, the right subtree of 32.
Sorry. 39.
39. Okay, so 39, I'll replace 32 with 39 here. Right? So the value 32, picture the value of 32 is basically 39. Everybody with me?
Yep.
Okay. All right, great. So the value of 32 is 39. Great. Next thing, what we want to do is, we've done a couple of things. We've done, let's write the steps we did. One, we found minimum value of right subtree right? Or child in that case. And we did replace value at root with minimum value, right? So we replace the value, so now 32 is 39, okay? And the last thing we need to do is now delete minimum value. When I say delete the minimum value, I'm referring to 39 here. Right? So what the tree will now look like after we've done all the deletion is, let me just put this here. It's gonna look like this: 39, 20, 18, 40, 40, and 51. Okay? And 32 is now gone. Okay? That's why I said it's a bit more complicated than scenario 1 and scenario 2. Because here we have 3 things to do, right? And we also have to write a function for finding the minimum value of our tree, right?
Wait, so Alex, is it of the minimum value within the entire subtree?
Yes.
Or?
Yes, the minimum value of the entire subtree. And being that it's a binary search tree, what would be the minimum value be? The leftmost node.
Mm-hmm. Yeah.
So far, so good?
Yeah.
All right, very good. Cool. Any questions before we jump into code?
See number 3 down there,
Oh, sorry.
the bottom of the screen.
Can you see it now?
Yeah.
All right, cool.
So if it was a bigger tree, right?
Yep. Like you
And
have,
it
like,
replaced the. Go ahead.
no, sorry.
Not like I'm gonna just look at it. Go ahead.
If it was a
I'm not-
bigger tree, like you mean like 39 has more values?
Yeah, like it went further down to like 31.
Okay.
Or what's the value up there? 32. If it went to 33,
So
like how do you shift the rest of them around?
got it. Let's
Or
keep
they
building.
don't.
So if we had 39, what's the other value? 51. And if that guy has more values, yeah?
Mm-hmm.
So call that
Like
30, whatever, 30. And call this guy, oops, gotta fix this a little bit. But that guy cannot have no values. Let's make this 49. Let's make this 40. Is that good enough or should we keep going?
I feel like I'm asking if it were bigger. So like if it were a bunch of values, does it shift the values like up or down, I should say?
It would save the values because as you see, like our 20 and 18, nothing happened to 20 and 18, correct?
Mm-hmm.
40 and 51, nothing happened to it, correct?
Right.
Right. So it doesn't matter what amount of nodes is attached to it. The only thing that's going to change is the minimum value, right?
Mm-hmm.
The minimum value goes up and the value we want to delete is gone.
Okay.
Right? Because 39 came up, correct?
Mm-hmm.
And 32 is now gone. So basically it's a replacement, but you have to deal with other things. It's not just the replacement, you also have to delete that minimum value as well.
Right.
Cool?
Mm-hmm.
Very good.
Thank you.
Very good. Any other questions before we jump into the code part of it? Okay, so let us jump into code.
Actually, Alex, I have a question.
Yeah, yep.
So in this case, a 40 just happens to have a left child. What if 40 didn't have a left child?
If 40 didn't have a left child, well, 40
Right.
would be the minimum value.
So you'd have to move.
I would just return. So my minimum function would just return 40 because there's nothing to look at. And then 40 would go up. 40 would basically go up where 39 is, and 40 would be attached to 51.
Okay.
Does that answer the question?
Yes.
Very good. Very good.
And just to clarify that point, 40 would retain its right child of 51 in that instance.
Exactly.
Okay.
Exactly. Because we're only retouching what we moved, and everything else that's attached to it doesn't get affected.
Right. It's still got that right child, and it will after the fact.
Yep. Exactly.
Okay.
Exactly. Cool. Very good. Good questions. So let's continue on. Here we'll just write. So write a function that takes, because that could be a question here. Write a function that takes a tree and a given value and deletes the value and returns a tree. Returns the modified. So this is what we write in here. We'll start off by writing a function. We'll call it delete. Delete takes in root tree node and takes in some value. We'll call it target value. Target value is an int because our tree is an int. Yes, it could be generic, but right now it only works with integer values and it returns us a tree node. Great. Start off with a guard statement, make sure there is a tree or nodes to look at. We'll just return nil if it's empty. We need to modify root, so we will make it mutable. Here we'll say var root equal to root. So this makes it mutable. And now we will check the target value to find out if we are looking left. So here, if target value is less than our root dot value, here we could force unwrap this. The only reason why we're doing that here is because we are guaranteed that we have a root. It does exist, so this is valid. So if the target value is less than the root value, where am I going? Where am I looking? Am I looking left or right?
Right.
Left.
Left.
Right, left. Who knows? It's like walking with my son. Move right, he goes left.
No,
Move
you're
left.
right. It's left. My
Okay.
bad.
No, it's fine. Cool. So if target value is less than root, we look left because it is a binary search tree. If it wasn't a binary search tree, that would be way more difficult, right? You'd have to go through every node in the worst case. Good. So here we'll say else if target value is greater than root value, then here we'll go right. Else, we found it, right? Found a node to be deleted. Okay. At the end of all this, we'll return root. And root here represents the modified tree after deletion. Great. So now let's go write the logic, right? So if I'm looking left, well, I'm getting echoes. If I'm looking left, I'll continue looking left here recursively. What is my function called? Delete. I'll pass in root dot left, and I'll pass in the target value. So here we're just using recursion to keep looking left, right? Because there's more things to look left, we'll keep looking left. Same thing for the right side, root right. Let's keep looking right, root dot right, and passing the target value. So those two scenarios is just happening to just call the function recursively until we've gotten here, right? Or we just return root. Great. So let's continue on. So we found it. This is where we go into our three scenarios. So scenario one. What's scenario one again?
If there are no children.
If there are no children. Very good. No children. Here we have one child. And we have scenario three, where we have both children. Great. Okay, so if we have no children, well, how can we find if we have no children? We'll say if right, if root dot right equal to nil, and root dot left equal to nil. And guess what? There's no children. What are we doing here on line 111? If we look back at our pseudocode, what did we say?
We're checking that there are no kids.
We've done left. That's for the no children. What's that?
Which one are you talking about?
Scenario 1, no children.
Right.
Somebody said,
Equal to nil.
somebody said, right? So root equal to nil. Thank you so much. Here.
Oh, okay.
Cool. And root equal to nil, this is why we have this variable here, or made it mutable. Now we could just set root to nil. This is good. Perfect. So this is scenario 1. Scenario 2, well, if we get down here, actually, let's just return root here. We'll change that if we have to, but for now, just return root because we are done. If we have one child, so we'll say if root dot left equal to nil, say else if here, else if root dot right equal to nil. One of the two things would be correct, not both. And lastly, we'll do the bottom one. So if the left is nil, well, we'll just say root equal to root. What do we say? Right? Yes?
Yeah.
All right. And next we'll say root equal to root dot left. Okay. We're just changing where root points to, because remember we're taking root out. Great. Now let's go down to scenario 3, where there's more work to do. What's the steps we said? Let's write them down here. Steps.
Alex, for scenario 2, so if it has a
scenario 2, let's go back to the drawing here. So scenario 2 here, we're saying if left equal to, well, let's say right, because there's no right. If right equal to nil, what do? We just say root equal to left.
Yeah, so how are we determining that it only has one child though?
Because we've passed through where it has 2 children. Actually, sorry. We've passed, 1 second. We're gonna do scenario 3 last here. Right? A mini?
Yeah,
Right.
Okay, I guess I'll figure it out as we go.
We'll test it out and then we'll see if we have any errors on our part here. But we'll take care of the last scenario last.
Okay.
Steps to delete. What did we write down? Steps to delete a node. Steps to delete a node. Steps to delete a node where. Let's do that here. Step 1, what did we say? We said, where's my notes? We said minimum. Right. Minimum value of right. Step 2, replace value at root with minimum value. And the last one, delete minimum. All right, so we have to get the minimum value of a tree, basically. Well, we need to write a helper function for that. Function minimum.
Why are you saying to get the minimum value of the right again?
Of the right subtree. If I go back to our notes here. So when we're trying to delete 32, right, we have to get the minimum of the right subtree, which was 39. Tiffany?
I was on mute. Okay, I get it. It's because that least value has to now become the new value to get rid of that value.
And to also
All
keep
right.
the order of our binary search tree correct.
Right. Right. Okay. Because if you mess with the first one, then it was okay. You're right.
It won't be a binary search tree anymore. Like the values, everything after deletion, the tree needs to be still a binary search tree.
Right.
And the way we'll confirm that, we'll use like in-order traversal or something to print out the values.
Okay.
Okay.
All right.
So very good. Minimum. Here we're just writing a helper function to find the minimum value of search tree. What do we know about the minimum value of a binary search tree?
It's on the left side?
It's on the left side. Very good. It's on the left side. So whatever we're doing here, we just have to keep looking left. Right? So here, the minimum value of 32, what do? We don't go right. We go left, left, left. We return 18. Everybody with me? Hello?
Yep.
Yeah.
If I'm looking for the minimum value of 10, I don't go right. That's going to get maximum value. Everybody with me?
Yep.
Yeah.
I go left, 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 left. I return 1. Same thing for 39. Looking for the minimum value of 39. Left, left, left. I return 18. Okay? Minimum value of 32. Left, left, left. 39. Good?
Yeah.
All right. So here we'll say current node equal to some root tree. And we'll use a while loop to say while let next equal to current node dot left. Right? While it's still things to look left, keep going. At the end, we'll return current node. Okay. And to address Cameron's question earlier, so if we have nothing to look at here, we just return what root is. Cameron?
Yes.
Right, I think you had a question earlier, right, that addresses that. So if there's nothing to look at, I'll just return what the current node is. Very good.
Got it. Thank you.
So very good. So now we have our next value. We just want to update. Here we just walk in the tree. We'll just say next here.
Sorry, can you just move up? Oh, okay, never mind. You're outside of that function entirely.
Yeah, it's a
My
helper.
phone disconnected, so I lost some.
Yep, it's a helper function. I'll pause here for you, for everybody to finish writing it.
Please, thank you.
Yep, it's a helper function to execute line 1. Right. So that's why I left deletion for later, because deletion is a bit more complicated than anything else. And then I highly suggest keeping notes and then doing it again yourself, going through the diagram again after lecture, as you're preparing for like interviews and all that stuff there. Because if you get a question like that, you know how to attempt it, how to do it. And again, it's not memorizing, it's just like drawing down what the tree looks like and then just going through it. How can I delete a node with 2 children? What am I doing? Am I going left, right? Okay, are we good here? We have current node. We're unwrapping left. If it has a value, we keep looking next. And we just assign current. So now current is the node after. And we just keep looking left. If there's nothing else to look, we just return current node. Okay. You could do the same thing for maximum by just saying look right. Everybody with me?
Yeah.
Yeah.
All right, very good. So now we have step 1. Let's go ahead and do so. Step 1. We'll create a temp node here because this returns a node. We'll say minimum root and pass in right, pass in root dot right. So this returns us whatever the minimum node is. Step 2 says replace value at root with minimum value. Step 2, root dot value gets assigned temp node dot value. And here we'll force unwrap this. We do have a value. That's okay here. And step 3, delete it. Delete minimum value and minimum value. So now our root dot write will be delete the root node, which is root dot write, and the value we want to delete is temp value. So unwrap this here. Okay, so this function will now take our minimum value. It's going to search the right subtree and delete it, okay? And return us that new subtree, which we have here. And if everything went well, if we have no errors anywhere, that should be basically what we went through with the pseudocode earlier, right? So again, the more complicated one is deleting a node where it has 2 children, right? Because you don't want to break out the tree and lose children along the way, because that could be done very easily if we're not paying attention to how we remove the nodes and how we reattach the subtree and reattach the subtree to the actual root, okay? Which is what we're doing here. Any questions before we test our code?
Can you just give me a few?
Yep. There's a tree head. How are we doing? Good?
Mm-hmm.
All right. So everybody has the helper function, yes? Well, if we don't have the helper function, this is gonna give us an error. All right, cool. Let us test this out. Let me go up here and let's just copy everything here and put it down below our functions. So just copy the tree, copy our test, or cut rather, and scroll all the way down. Let's put it down here. Before we do anything, let's just make sure this still works. So run the playgrounds. We should get 51232. 51232. I'll just remove things we don't need. Okay. So the reason, again, we get into 51232 because what? This is a binary search. If you use in-order traversal on a binary search tree, it's guaranteed that the numbers should be ascending, right? Write that somewhere or just make sure that we know what that is. We actually write that down. So if using in order traversal, print order of the elements to be ascending. Right. Any questions about that? So after we delete and we print again, it should be ascending. If not, we have an error somewhere. Everybody with me?
Yeah.
Yep.
All right, cool. So 51232, let's add some more of the numbers in here. Let's just add all the numbers we have. Root.
I'm sorry, Alex. Can you just explain and I see the function in order traversal, and it says left dot in order traversal. Like, can you just explain that again for me? Because I wasn't here.
Do you recall traversals on a tree? Like we had 3 depth traversals. We had in order, pre-order, and post-order.
Yes, I do.
Right? So the in order traversal we wrote here is basically a way to go through all the nodes of a tree. And the way we went through it, right? We went left, right? Left first. That's the current node 12, correct?
Right.
So we go left first, then we go root, and then we go right.
Right. I'm just how it's set up in the function. Can you like in this right here? Can you explain what exactly it's doing?
So it visits left, right? It prints the value. It visits right. Well, it visits left. It prints the current value, right? And it visits right, and it just keeps going until it's all done with the tree.
Okay, so okay.
This is calling the left function, right? It calls the left. It prints the node. When it's done, it just prints the current node. Current node is value. Right.
I'm understanding what you're saying, but I'm just not seeing how the function, how it knows to do the left dot in, like how does it even know to just?
Well, that's recursion, right? Recall back when we spoke about recursion. This is calling the function again until there's nothing else to look at on the left side. Left here represents the actual tree's value, left.
Oh, all right. So I'm sorry. So left is basically a tree node. It's just calling the function because it's inside of that class. Okay, sorry.
No, that's okay.
I get it. Because at first I thought it was a separate function. That's why I was like, how does it know? But it's
inside it's on the class itself.
I see it now. Thank you.
Yep. Okay, so where were we? We're trying to add nodes, right? Let's see. With the tree we started off with was 12, 5, 32, correct? Okay, so let's add in 3. Root, insert 3. Root, insert 11. Root, insert 32. We have 32 already. 15. Root, insert 13. We had 21. We had 40. We had 50. We had 35. And 65. Okay. So those are the nodes of our tree. And if again we print it out, it should be ascending order. Let's go ahead and print. 3, 5, 11, 12, 13, 15, 21, 32, 35, 40. Verify we have this before we continue on.
Got it.
All right, perfect. Everybody has this? All ascending order?
Yeah.
All right, cool. Now let us go ahead and, does this have a, we use Terminator, right? Okay, so if we use Terminator, let's just break the Terminator for now. Let's go ahead and now delete. Call our function delete, pass in root node, and we want to delete 32. After we delete 32, we'll just call our print. We'll call our print function again. We don't need this here. I'm just putting print here to break the line. Everybody with me? Hello?
Yeah.
Yeah.
Right, because we have a terminator in our, in here we have a terminator. Everything is gonna get printed on the same line. But now I don't want to also have our order print statement happening in the same line. So I'm actually just adding in a new line.
Alex,
Okay.
can I insert for a second? The numbers inserted for like 1 second.
Say that again.
Yeah, right there. Just the numbers that we inserted.
Oh, the numbers?
Okay, thank you.
Mm-hmm.
Okay, I got it. Thank you so much.
All right, cool. Everybody else okay here? Yes.
Yep.
It works.
What? Oh, you deleted already?
Yeah.
Okay, ahead of us. All right, let us test on our end. Print. Stop. Run. Okay, so here 32 is gone. We have one less node. Everybody with me?
Yeah.
Okay, so this was the more complicated deletion. Let's see something easier that should just work as well, like 65. Let's just do it on a new line. Delete 65 and print again. Here we need the print so that we don't have everything in the same line. So delete 65, this is no children. This is both children. This was scenario 3, right? Scenario 3. This was scenario 1. And let's test this before we continue.
Wait, quick question. Since we're
60.
just inserting, how do we know when they have children or not from what we drew out?
How do we know if they have children? You mean when we inserted here?
Yeah, like when we're inserting, how do we know whose child?
Well, our algorithm that we wrote for insert does that, right? So when we insert, I highly recommend watching the video before this one. But when we insert, for example, when we're inserting something, we check the value first. We're like, hey, are we inserting left or the right? Like if I have.
I understand that, but I'm saying like when it's listed like that, and when you like how you saying here that this one has no child, this one has one child. This is from what you drew.
Oh yeah.
So
Sorry.
you know.
Yeah.
But in something like this, how would we know?
Oh, you mean like just like randomly like this?
Yeah.
There's no way to know unless you know what the tree looks like. Yeah.
But the whole idea is that's why the whole idea is to just guard it for all of them because you wouldn't know who does or who doesn't.
Yeah, exactly. Because at the end of the day, if you write an algorithm, that's why there's so many tests when you do leak code, right? Because you got to test all the scenarios. Like, hey, there's nothing in the tree, right?
Right.
There's one thing in the tree. There's two things in the tree. Three things in the tree. There's a million things in the tree. Will it still work?
Gotcha.
Yep,
Alex, I think I broke it. I tried deleting 50 and it gave me like this error saying it was nil.
50. Let's see. Scenario 1, 2 children. And let's test it on root. In order. Delete. So we tested for no children. That worked. Let's do root node 50. What is 50 live? 50 is now somewhere. What is 50? 50 is 50 would be no children as well, right? If I removed 65. So 50 is
This was I did this before removing 32 or 65. I just wanted to test that.
Okay, so you did it here.
Mm-hmm.
So in that case, 50 is scenario 2. One child. And root. In order traversal, print.
I got an error as well.
Yep, let's see what's going on. So here, one child. And let's see what the error is. Found nil. Somebody is not happy. We banged somewhere. So this is one child. One child. Where are you? One child here. I'm not unwrapping anything here. $108. 108 here. Oh, here. All right. Let us just do this. Replace value at minimum. So here, root value. I don't want to replace anything. Scenario 2, replace value. So now this guy needs a value. Let us do. So basically node is nil here. So.
But why is it nil if there's still so many numbers left?
1 second. So what's happening here, let's see, temp node is nil here. Because that 50 doesn't have, let's see. 50 doesn't have a minimum. Is that our minimum function? Is it broken here? Let's test this. Because what it's doing, it's trying to, we are at 50. We're trying to delete 50. Let's just do this in code here, in pseudocode. We're trying to delete 50. So 50 has one child. And what should be happening is 40 should now be connected to 65. 50 should be returning 65. 50 should be returning 65, replace, no. I think we're missing something here. It should not get down here, period. Let's see, return root here. This wasn't an else statement, wasn't it? That wasn't in an else statement. This is the problem. That whole thing should be in an else statement. Else, this, right? Okay, let's test this.
Wait,
Okay.
whether you put just the let temp node, that's all in the else statement, just that?
Yeah, that whole scenario should be in an else statement. We only do that if—
The 1, 2, and 3, right?
Yes. Good catch there. Cassandra, was that Cassandra?
Yeah.
Very good. Excelente.
So hold on.
Because what happened,
So
it was still falling through here and it was trying to do our both children scenario. And we don't want it to do our both children scenario, right? We only want to do, if it's one child, just do the one child scenario. Don't do the both child. It was trying to attempt like 50 here, was trying to do the both children scenario.
Can you go back to it?
You wrap scenario 1, 2, 3, sorry. Steps 1, 2, 3, or scenario 3 in an else statement.
Okay, so the first, so scenario 2, that's its own else.
Else if, yep.
Wait, all right, can you go, because now I'm confused. Okay, so if target, can you move up a little bit? Because my else blocks are like,
the first
that
one is
else block.
That
so
there's
in
one
that
there's
else block.
Yep, there's one whole else block.
Right. There's one whole else block. Okay, good. But inside of that else block, you
There's
have
the first if checking for no children.
right, and then the else if for
The else
root.
if for the left or the right.
Oh, see, okay.
This right.
And then after that, there's another else inside.
For the more complicated deletion, for the one where there's both children.
Okay, and that. So how do we know when to put all of that in? Hold on, wait, let me. So that's in this, and okay, well, okay, that's what you say. That's what it is. Sorry.
No. If there's any questions, let me know.
how do you know? All right, so it's in one big else block, but inside, because the else, what my thing is that when the else and the ifs are not connected, it confuses me. So you have the else if, else, but they're not connected. You separate them. So
oh, you mean like when you say connected? What do you mean, like this?
I'm gonna just do it the way that looks.
What,
What do you
mean, like this? Like something like that? Whatever, like this?
No, just the one on the bottom that's connected to that. That last else, but it just doesn't look like.
Else if left is nil, else if right is nil, else it has both values.
Okay, I got you.
If it has both values, then execute our
what's
both.
inside.
Yeah.
Got you. Let's run it. Okay, it works.
Because what was happening, right? That could be a good bug exercise. What was happening here? It was still doing this logic because we have no return here. If we had a return root here, it would just like return, not do anything else. You got me?
Right.
But because this was not wrapped in an else statement, it would still try to execute this. It's trying to get the minimum of 50, and 50 doesn't, where is it? It returns nil here because 50 doesn't have any more because we, minimum of root, it returns 50, it returns 65, right? But here we're trying to now force unwrap something that doesn't exist.
Okay.
Okay, because if we go back, that's where we kind of picked it up here. If we go back here, we're trying to delete 50, right?
You
with me? And 65 doesn't have any children.
Right.
And it returns nil, correct?
Right.
And then in here, it returns nil. So temp node is nil, right? And here we're trying to force unwrap something.
And then get the right of it where we don't have a right of it, right?
Right, it doesn't exist, like it's nil. And we're trying to say temp nil that value, and it crashes the app here. That's why you gotta be, well, I guess that's a good, it causes to see our error, first of all, but that's why using force unwrapping, you have to know exactly, like I am guaranteed to have a value, right? I'm only guaranteed to have a value if there's both children, correct? But if I'm trying to execute something where there's no children, it returns nil. So this is our error of crash here. And then we had to wrap this guy in our else statement, which we did not do earlier. So now it only comes in here if left and right are both have values.
Got you. Okay.
Cassandra?
And that's inside of this else.
Yeah.
Any more bugs for us?
Just that one I found.
All right. Cool. So you did exactly the correct thing, Cassandra, by the way. You check all your edge cases here, which we were probably going to get to at some point and see the crash. But you check your edge case for one child, and that's why it crashed earlier, correct?
Yeah.
Right. So we have to check all edge cases before we're like, oh, my solution works, right? So edge case number 1 is working. We're able to take out 65. 65 is no longer here. Case number 2, we're able to take out 50. 50 is no longer here. And the last case, 65, which is no children, this should be easier. We're able to take out 65 here. Okay? And you see how complicated this is. So I would strongly advise, as it's still fresh, to like redo it again, right? Redo it again, and that'll give you a better hold onto it there. Yes?
Yeah.
Any questions? Everybody took the notes down, correct? Like drawing the tree as we went?
Yes. Alex, I have a question.
Yeah.
Would you be able to explain one more time? I didn't really understand why we needed to put the temp node in else.
The temp node in else. This guy.
Yeah, that part.
Because we needed, so basically what we did here, if we went back to, where is the one we used? Not this one. This guy here. Our temp node is 39. Do you see what 39 is right now? Sorry. This is our temp node here, this guy.
Okay.
Right. because that temp node, we have work to do with it, right? We have to get its value. Then we have to pass its own value. Because right now, we replace temp node's value with the current root. So if we go back here, we get the temp node, we take its value, we put it in the root value, correct? This is what we did here. We took 39 value into the root. So far, so good?
Okay. Yeah.
And then we also use temp value here because we don't want to erase temp's value at any point. Because if you see, right, we don't want to erase temp's value at any point. We want to get temp's value here. I mean, you could just like say not use temp value and go directly to root's value, but it's just like the next thing, just using a variable to make your work easier. And the explanation of it easier as well.
Okay, yeah.
Okay, but temp value represents 39 here. And we were able to get 39 from down here because that's the minimum of the subtree.
Okay, I see.
Okay. It's just a hold on that value and then we use whatever we want to do with it.
Yeah.
We could have just done this directly in here and remove that line. You see what I'm saying?
Yeah. I mean, it's just easier to see when it's placed into the temp node.
Yep. All right, so this is the more complicated.
Can I see above that?
Above that here.
Yeah, I'm pretty sure it's mine because I'm not deleting anything, so I'm pretty sure it's my if statement.
When you say you're not deleting, you got the first one here, this one? Actually.
Yeah, I just think it's like my positioning, like something's out.
You have the one else statement here, yeah?
Yeah, sorry. But can I see it from the top, like from the root variable? Yeah.
Do you add the in order traversal function to display the new changes after each time?
Yeah, and then put a print statement after it, an empty print statement. Eric, you want me to go down?
Hold on.
Yep. Did somebody try to delete all the notes?
Scroll down a little.
Sorry. Scroll down a little. I'm going all over the place.
There's something else wrong there.
You have scenario 1 taken care of inside your else statement. You have scenario 2 taken care of, right? And you're not saying left here, right? You're saying right for left. If left is nil, just make right the root.
If left is nil, make right the root. If right is nil, make left the root, correct.
Yep, and then you have your last else statement here.
And that's with the temp node. Something wrong. I know when I do the I'm about to tell you, like when I do 32, it makes
32.
My 32 position 5. So like on your read on the bottom, the top line. Now go back. The bottom of Xcode.
Oh, the bottom here.
3, 5, 11. Yeah, you see where you got 32, 35.
32.
Mine's
35.
after I do it, it says 35, 35.
Oh, you have 2 35s. So it looks like you're
like
there's definitely something wrong in this chunk of code here. What's your minimum thing look like? This guy, the minimum function. Is it all the same?
Yeah, it's the same thing. Looks the same to me.
Because it's not your minimum returns of value here. You get the value, you put it into root, but your delete itself, in your delete, are you passing root that, right?
My delete.
On line 113.
On step 3, right?
Yeah.
Yeah.
Anybody else having deletion issues? Because other than that, I'll take it offline with you.
All right.
Hello? Anybody else having errors deleting or logic errors deleting?
No.
Okay.
No.
All right, so I'll wrap it up here. And then Eric, I'll take you offline to help you.
Okay.
All right. Okay, cool. So the most important things here, make sure you're able to I'll probably say redo what we did today over the weekend to understand how to delete, because deletion on a tree is more complicated than anything. insertion is you insert directly, but deleting, especially where you're deleting a node with 2 children, that's like the complicated part of it there. So like just understanding that there. And go back and review the traversals, right? In-order traversal, pre-order traversal, post-order traversal, and breadth first traversals, right? So know our traversals for binary trees in general. Okay, very good. Any questions before we conclude? Any questions?
No.
Okay. So everybody was able to get the notes we drew out, right? Nobody needs that shared out, right?
No.
Okay. All right, cool, perfect. Thank you, Brandon. You don't want to see my drawing, huh? I got you.
No, that's not it.
I got you.
I
You're
don't
a
mind
fantastic
that.
artist.
What's that?
You're a fantastic artist.
You're right. Okay. All right, cool. Awesome. So we'll end here and we'll catch up later.